Have you noticed how AI image generation is getting just impossibly fast? Well, there's a new technique behind it all, and it's called flow matching. It's the engine powering top models like Stable Diffusion 3, and in this explainer, we're going to break down honestly, the deceptively simple trick that makes the whole thing work.
Okay, let's not waste any time. Let's just get right to the payoff. On the left, you've got your traditional diffusion models, right? They need, 10, maybe 20 steps to cook up an image? But on the right, that's flow matching. We're talking 2, maybe 3 steps. I mean, this isn't just a little better. It's a completely different league. It's a massive leap forward. So the big question is, how on earth did they do it?
So, what's the big secret algorithm behind this insane speed boost? You're not going to believe it. It is almost shockingly simple. Seriously, you just pick a real image, pick a sample of random noise, and then you just draw a straight line between them. That's it. The model's entire job is to learn the constant speed it would take to travel that one straight line. And that's the whole thing. It feels like it shouldn't work, right? It's too simple. And that's really the mystery we're diving into.
Yeah, that simplicity, that's the core puzzle we're going to solve together. I mean, how can a recipe that basic create these incredibly complex, beautiful images? It just doesn't seem to add up. To get the answer, we've got to dig a little deeper. We need to start with, believe it or not, the fundamental physics of how an AI actually creates anything. So, try to think about generating an image less like a computer process and more like a physical one. Imagine we have this big cloud of random staticky noise. Our job is to transport every single particle in that cloud, guiding each one until the whole thing settles into a coherent work of art. This idea of transport is going to be super important. Okay, so to make a journey like that, what do you need? You need a map. And the AI needs a map of the entire universe of possible images. In the lingo, this map is called a probability density. Just picture it like a huge landscape. You've got these low, flat, boring valleys. That's all the meaningless static. But then you have these towering mountain peaks, and those peaks represent every possible meaningful image that could ever exist. The AI's whole goal? It's to learn the trails, the paths that lead from those noise-filled valleys all the way up to the image-covered peaks.
Right, so how do you actually travel across this giant map? Well, you do it with something called a velocity field. The best way to think about it is like an invisible current or a wind that's constantly blowing, and this wind is so perfectly calibrated that it pushes every single particle of noise in exactly the right direction. So the AI's real job, its only job really, is to learn the shape of this incredibly complex current, this velocity field, that can turn a cloud of static into a picture you'd recognize.
Now, before we can really appreciate the genius of flow matching's little trick, we first need to get a handle on the problem it solved. So let's take a quick look at the old way of doing things, which was, frankly, incredibly expensive and complicated. So these older methods, like continuous normalizing flows, or CNFs, they had this one massive problem. There was no simple right answer for the model to learn from. There was no ground truth. So to train the AI, you had to take a finished image and run this super expensive full simulation in reverse, just to try and guess the path it might have taken from the noise. As you can imagine, this made every single step of training unbelievably slow and computationally expensive. And that's exactly why those models they never scaled up. And this is where flow matching just waltzes in and pulls a rabbit out of a hat. It pulls off this little magic trick that completely sidesteps that whole expensive reverse simulation thing. How? By creating its own ground truth, using nothing more than those simple, straight lines we talked about at the beginning. Really, the core innovation here is basically giving the model a cheat sheet. For any given point on that journey from noise to a final image, flow matching just hands it a simple, correct velocity. It says, here's the right answer. And that means instead of all those complex simulations, the model can use a much, much faster and more direct way to learn. And how does it make this magical cheat sheet? You guessed it. It's that same ridiculously simple recipe. It just pairs up a random piece of noise with a real image and tells the model, hey, the correct answer is easy. It's just the velocity you'd need to get from point A to point B in one single straight shot. It honestly feels a bit like cheating, doesn't it? And maybe it is. But wait a second, this super simple recipe creates a massive paradox. Think about it. Any single point in that noise space could be on a straight line path to thousands of different images in the training data. So that means for the exact same input, the model's being told to go this way and no, go that way 1,000 different times. There are thousands of conflicting correct directions. So this brings up a really important question. Are we just training our model on complete and utter garbage? And the answer, which is pretty amazing, is no, we're not. And the reason why reveals the absolute genius of this algorithm. It turns out that all of that so-called garbage is exactly what the model needs to learn the right thing. Okay, so the first piece of this puzzle is understanding how the model actually learns from its mistakes. This is all controlled by something called a loss function, and in this case, it's mean squared error, or MSE for short. Now, its main job is to measure how wrong the model's guess is, but the real magic is in how it pushes the model to get better. See, when a model that uses MSE gets hit with a bunch of conflicting directions for the same input, it doesn't just crash or get confused. Instead, it does something really clever. It finds the single most mathematically efficient way to reduce its overall error, which is to learn the average of all those conflicting instructions. And here it is, folks. This is the punchline, the grand reveal, that average of all those simple, straight, and technically wrong paths, that average is the complex, curved, and ultimately correct path we were looking for all along, the path that guides noise into a beautiful image. So those conflicting labels, they're not a bug. They're the entire feature. That's the secret sauce right there. Okay, but why is straight line? That seems so random. Well, it turns out that's not arbitrary either. It's actually rooted in this deep mathematical principle called optimal transport. The name kind of gives it away. It's all about finding the most efficient way to move stuff from one distribution to another. And when you're moving from a cloud of random, evenly spread out noise, what mathematicians call a Gaussian, to a single target image, the most efficient optimal path is, you guessed it, a straight line. So let's just recap this, because when it all clicks, it's really beautiful. That straight line path that seemed totally arbitrary, nope, that's just optimal transport in action. Those conflicting labels that looked like garbage data, turns out they're the genius part. They get averaged out by the MSE loss function to create the true curved path. You see? Every single step that looked naive on the surface is actually backed by some really deep, principled mathematics. All right, so now that we've kind of pulled back the curtain and seen the trick, the next logical question is, can we make it even better? And the answer is a resounding yes. And this is what puts us on the road to the Holy Grail, generating a perfect image in just one single step. Remember how we said averaging all those straight lines creates the true curved path? Well, that very curvature is the reason we still need to take a few steps at inference time. The more curvy the path is, the more little baby steps you have to take to follow it accurately without getting lost. And that very problem leads us to the next big innovation, something called rectified flow. The logic here is actually pretty simple. If pairing random noise with random images creates curvy paths, what would happen if we pair them up more intelligently? So rectified flow uses a first model just to find a better starting noise for each image, a starting point that's already a much better match for the final destination. And when you do that, you create pairs that naturally have much, much straighter paths connecting them. And the benefit there is pretty obvious, right? Straighter paths mean fewer steps. It's that simple. And if you repeat this reflow process a couple of times, you can make the paths so incredibly straight that a new model can learn to jump from start to finish in a single leap. And that gets you the raw speed of a GAN, but with all the stability and quality that comes with flow matching. When you look at the timeline, it really puts the speed of all this innovation into perspective. I mean, for years, we saw slow, steady progress. Then, in 2023, flow matching just shows up and completely changes the game. And in the tiny amount of time since then, we're already onto the next evolution with rectified flow and real one-step models. The pace of progress here it's just staggering. So this all leaves us with one last really fascinating thought to chew on. Flow matching proves that if you average out a whole bunch of simple, maybe even wrong little rules, a much more complex and elegant truth can just emerge. And that begs the question, if this principle is so powerful here, where else could we apply it? What other huge, complex problems out there might just have a deceptively simple solution hiding